I'd like to work out an example involving the multipole expansion for the electrostatic potential of a charge distribution. I hope that this will show you how this expansion can be useful in a practical problem and indeed how to do the calculations. So you can see that the problem amounts to finding the first few terms in the multipole expansion of V for a uniform ring of charge that has radius r and charge q. And we want to do this at a special point on the axis of the ring, a distance r away from the center. Once we do this, we want to compare our result, which will necessarily be an approximate result, to the exact result, which is not too difficult to find for this kind of a simple case. So we start doing the calculation term by term with the monopole term in the potential, V mono, and this is given by the familiar 1 over 4 pi epsilon 0, but then there's r, which is the distance, times the integral, which in a three-dimensional problem would be rho times d tau. But in this problem, we don't have a three-dimensional charge distribution. We actually have a one-dimensional charge distribution where the charge element, dq, is given by some sort of charge per unit length, lambda, times the length element that we'll call dl prime, using the prime coordinate system to indicate the variable of integration. So the integral then is simply lambda dl prime, which is about the simplest kind of integral that you'll ever encounter in a problem like this, because all it really is doing is adding up all of the charge elements around the ring as we integrate around the ring, and that will simply give us the total charge, which is q. So that's q, and the result that we get for this is the familiar term that looks like the potential due to a point charge, q over 4 pi epsilon naught r. And that makes sense if we look at the picture, because the very first term would be approximated by the potential of a point charge, a distance r away. Now that's not the exact result, because not all parts of our charge distribution are a distance r away. In fact, they're always a little bit further than that. And so this term, if we were to stop here, would be an overestimate of the electrostatic potential. So we would expect our correction terms, the higher order terms, to give us something that's smaller. And we'll find out as we do this. So let me create a little bit more space here and get rid of my charge element. We know what that is already. And now let's move on to the dipole term. All right, so from the formula that comes from the expansion, the dipole term is as follows. It's got the 1 over 4 pi epsilon naught out in front, but now we have r squared, the distance r squared, followed by a slightly more complicated integral. Get rid of the q here. And this integral is the integral of r prime cosine theta times lambda dl prime. And to make sense out of this, I first have to go back to the picture and define the distance r prime and the angle theta. So r prime, remember, if the origin now is the center of the ring, r prime is the vector that locates the charge element with respect to the origin. So that arrow that I've drawn in there is r prime. And the angle theta is always the angle between the r prime vector and the r vector. And just as a little bit of a review, the r vector goes from the origin to the point in space where we're trying to find the potential. The r prime vector goes from the origin to the element of charge that we're considering, which is the little dq that I've indicated on the sketch with a shaded arc. So the angle theta is the angle between r and r prime, and in this particular situation we see that that angle is 90 degrees, and it will be the same no matter which charge element we're talking about. All the way around the ring, that r prime vector will always be perpendicular to the r vector. And so right away we see cosine 90 is 0. So the dipole term completely goes away here in this expansion, which is interesting. All right, there's no dipole moment for this charged ring. And what we need to do now is move on to the quadrupole term. And this is going to be a little bit more complicated, so I need some more space. I'll go ahead and clear out some space for this. The quadrupole term now, which apparently will be the most important correction term for our approximation that goes beyond the point charge result, V quad, once again, has the 1 over 4 pi epsilon 0. In this case now it's r cubed. And the integral, just a little bit more complicated now, has r prime quantity squared. I'll put parentheses around that just to make sure that we don't confuse that. And the Legendre polynomial, we need now the second order Legendre polynomial, which is 3/2 cosine squared of theta prime minus 1/2. Once again, we have lambda dl prime. And so this is an integral all the way around the ring of that quantity there. It simplifies, though, right away, because we've already pointed out that the angle theta is 90. And so cosine of 90 gives us 0 again for that term. And so what does this reduce to? We've got 1 over 4 pi epsilon naught r cubed integral of, well, there's now a minus. I can put a minus sign out here. There's 1/2 or r prime squared over 2 times lambda dl prime. What do we do from here? Well, it's a integral over all of these elements of charge. And we have to ask ourselves, does the r prime value change? And remember, this is just a magnitude. And the answer is no. Everywhere around the ring, r prime has the value capital R, the radius of the ring. And so that can actually come outside the integral, along with the factor of 2. So we're almost done. This is turning out to be much easier than it originally looked, and it's often the case in physics problems. We've got minus capital R squared. That comes from the r prime squared, all right, over 8 pi epsilon 0 little r cubed. The integral that's left now is indeed just about as simple as they come. Once again, lambda dl prime, which integrates out, as we found in the monopole term, to q. So we get minus q r squared over 8 pi epsilon naught r cubed. That's our quadrupole term. So we're not going to go any further for now. We'll stop at this, but let me just summarize then what the overall answer is. So I'll clear some space out for this. We can see what this is right here. I want to put the monopole term and the quadrupole term together in one expression, because our next step in the next clip will be to compare this answer, which is approximate, to the answer that we would get from the exact calculation. And we'll see how good the approximation is. So now this is approximately, we'll write this as V mono. The V dipole term drops out. We'll just remind ourselves of this. V dipole term is 0. Then the quadrupole term, we've worked these out. So we get Q over 4 pi epsilon naught r. Right, that's what we expect if we had a point charge. And then we said before that that first term is actually an overestimate, which makes sense because the quadrupole term that we calculated was negative. So we get Q capital R squared over 4 pi, whoops, excuse me, that's an 8 pi. I'll fix that. 8 pi epsilon naught little r cubed. So the second term, the quadrupole term, is a correction to the first term. It brings it down. That makes sense. The only other thing we could do at this point, before we compare to the exact result, is we could check the dimensionality to make sure that we haven't made some kind of mistake in the algebra or the calculus. And that turns out to be correct as well, because look at the first term. In addition to the 1 over 4 pi epsilon 0, we've got a charge over a distance. And we know that that's correct for the right dimensions of electrostatic potential. And the second term, we have the q, we've got the pi epsilon naught, and again, the combination of the two lengths in the numerator and denominator gives us 1 over a distance squared. So that much checks out, and we'll see in just a minute how this compares to the exact answer.